So, welcome back to the Layers channel, and today we're based in the ceramic area of the National Centre for Additive Manufacturing, and we're going to be talking about a cool project we did with a couple of companies, namely Domin, Addup and Solukon. To talk about that, we've got Chris, who's a research engineer here at the Additive Manufacturing team. Chris, do you want to say a bit about yourself and then a bit about what the project actually is?
So my name's Chris. I'm a research engineer here at the National Centre for Additive Manufacturing. I work across a lot of laser powder bed fusion machines and electron beam melting machines. But today in particular, we'll be talking about a project to manufacture servo valve bodies with a company called Domin using a machine called the Addup Form Up 350.
Oh, fantastic. So for those that don't know, Domin Fluid Power, they create direct drive servo valves, and they're used in the hydraulic industry. And they're used across a wide variety of applications, from testing to industrial uses such as stamping and pressing, or even in robotics, in marine or in maritime. And one of the pretty cool things about the Domin parts is that they're using all of the advantages of additive manufacturing, whether it's using complex, optimized internal geometries, or whether it's consolidating parts. And they've been really quite successful with it. Compared to conventional parts, they've been able to reduce part weight by 25%, reduce parts by 40%. They've achieved a 25% higher flow rate, 400% smaller, and also 200% faster as compared to a standard direct drive servo valve. And so this really shows some of the possibilities of additive manufacturing combined with some conventional processes to create a really useful product which is in a market which is probably quite fair to say has been a bit stagnant, but also has global applications in terms of its size. One also really neat thing that Domin are looking to do is over, up to 2030, they're aiming to save 1 gigaton of CO2 every year, which in today's climate of sustainability and net zero is a really good initiative. In this video, what we're going to be going through is a sort of run through of how the parts were created. Now, bearing in mind, Domin aren't locked into an Addup Form Up. Domin were using the MTC to test out a variety of different bits of kit. It's one of the things we offer at the MTC. We've got lots of different AM machines that companies can use, and that was one of the benefits we saw running this project, is we were really keen to see how that particular machine would deal with such complex internal geometries with low overhangs, and then also conversely how the Solukon would deal with removing powder from the part. As I say, it's got lots of internal geometries, and that's really difficult to get powder out of. So for both of us, it was quite an interesting learning experience. So in the video, we're going to go through all of the build, the debuild, removing the parts, and also then putting them in the Solukon. And we're going to talk through that to give you a little bit of behind the scenes of some of these processes, because they're not often seen. And so without that, let's go to the video. So what's happening here, Chris?
So this is the machine that we've been using, the Addup Form Up 350, which is a modular additive manufacturing machine dedicated to building using metal powders. We're currently using this machine to manufacture servo valve bodies from Domin Fluid Power. So, nice. As I mentioned, this is a laser process. The umbrella term, you might say, is laser powder bed fusion. So what we've got here is a layer-by-layer process. So the laser will come over and melt a single layer of powder, and after that, a new layer will be deposited, and the whole process will start all over again. In this instance, our layer thicknesses are very small, only about 45 microns. So as you might imagine, we've got a lot of layers to get through, and this process is quite a lengthy one.
What are some of the features of this machine, like in terms of build size, amount of lasers?
So you can build over quite a large build area. So the plate that we're looking at now is about 350 by 350 millimeters, and the benefit of that as well is that you can build over the entire plate. There are no holes or struts that you have to avoid, which you have to with some other machines.
And dual laser?
Yes, dual laser. As I mentioned, this process can take a very long time. The parts that we're looking at now are only about 60 millimeters in height, but you know, when you're building layer heights that are only about a human hair in thickness, you know, we're talking about 1,300 layers across this whole process. So that's a 40, 50-hour process. So as you can imagine, having 2 layers melting at the same time can really bring that build time down and hence increase the efficiency of your production.
So do you want to say a little bit more about what's actually happening on the screen now?
So what we're looking at now is the melting for a single layer is about to finish. There's a camera that takes a photo of the layer, and the structure you see moving across there is actually spreading a new layer of powder across the plate.
Oh, what kind of recoater does it have?
So typically in machines you might have a recoating system that's a blade or a rake or a brush, but this one is actually a little bit different. It uses a roller, which spreads the powder across the plate, maybe a little bit like a rolling pin.
Yeah.
And the benefit of that is that the powder is sort of being nicely organised and spread gently across the plate, which really offers 2 significant benefits. Firstly, it allows a build of excellent surface finish, so we're getting really good surface roughnesses, potentially up to 5 microns RA, and with that a very good resolution of parts. And the second really significant benefit is that the amount of supports that we need in our build is much lower than with some of our other machines.
And is that enabling features such as heat exchangers or complex internal structures such as, I'm thinking, really thin walled pipes or channels?
Yep, heat exchangers, lattices. One of the main benefits of this machine is that it can build things like complex cooling channels, which might be a real benefit when we're coming to create complex custom-made tooling. So if we can build in custom cooling channels into those geometries, we can potentially get some really good benefits out of that. You know, combine that with the use of materials. We're using maraging steel in this machine. Combine that with the requirement for not as many supports. Add that to a very high quality surface finish, and you do have a machine that is well suited to tooling. So here's our operator Max. The build has just finished, and he is in the process of unloading the powder and the build from the machine. Now, one really important thing to remember about this process is that the overflow and the waste powder is not just thrown away, it can be reused. So that's the first step of the debuilding process. Max is retrieving the overflow powder from the machine, and that will go back into the next process. So this is the overflow waste hopper from the previous build, and to turn around for the next build, that hopper will be reused and recycled as the powder used for the next build.
And is it a simple top-up process, or does this go through any blending or sieving?
So what we're using here is a very fine particle size, and that helps with the high resolution and good surface finish, which I talked about earlier. So in order to get that powder free-flowing, ready for the next build, we do take it through a sieving process. And actually that sieving mechanism is one of the modular parts of this machine.
And we should also say it's very important, the cleaning aspect that Max on screen is doing. Contamination is one of the sort of key things you have to make sure you prevent. And so Max here is just making sure that anything that shouldn't be on there definitely isn't. He's using alcohol spray. We
have to make sure these things are clean, and we have to make sure that the process stays under argon as well for as long as possible. Any oxygen or other contaminants that are getting into that powder will potentially spoil the properties. So Max has removed the hopper from the machine and he's placing it into our next module, and that's the vacuum module. So the hopper is going into the bottom of that machine. So Max is putting the hopper into the vacuuming module for the Addup. So the powder which is deposited on the bed during the build across hundreds and hundreds of layers doesn't just disappear magically. We need to be using this module here, which is the vac clean module, to remove all that powder and hopefully unveil the finished build. So Max here has inserted the waste hopper, the recycle hopper, into the vacuuming system, and now we're installing the inlet and outlet hoses into that, which will draw out the powder. Again, very important that this all stays under argon in an inert atmosphere to prevent oxidation. So at this point we get to use one of the Addup's inbuilt features. We're essentially using it as a glove box. So Max is removing the gloves here, and we're doing this to prevent exposure of the powder and the powder unit to air as much as possible. So remember those hoses that we inserted into the machine earlier? We're now using those to dig out the powder, to remove and recycle all of the several kilograms of powder which have been used throughout the build. So as you can see, we've got the nozzle in there, which is removing all of the powder from the internals of the machine.
And does this machine only deal in margarine steel, or can you change the material?
This machine, at the moment, this machine is dedicated to maraging steel only. However, you can change the material. However, if you were to do that, that is subject to an extensive clean down process. We're always thinking about contamination.
Yeah, fair enough, fair enough.
The powder vacuuming process is almost complete. Just getting the final bits of powder out of this build as much as possible, and now retrieving the build and the plate from the machine. So it's as each layer gets deposited down, the plate sinks further into the machine. So what you saw there is the plate rising back out of the machine.
No, that's awesome. How many parts were on the build, and what sort of time did it take to actually build all these?
So we decided that we could fit as many of the parts as possible as we could on the plate for this build. That's not always the case, but in this instance we decided to fill the build as much as possible with 22 different parts.
Ooh. And what are some of the considerations you have to take into when you're placing those parts on the build?
So it's really important to place the parts to make the build as risk-free as possible. So we're trying to reduce the use of supports, to reduce the we're trying to reduce the number of supports that we need during the build. We're trying to prevent any harmful interactions between the recoater and the parts themselves. Carefully placing any thin wall samples or narrow samples. So there are lots of considerations. You can see that all of the parts there are actually angled slightly. That's to prevent the recoater coming along and hitting all of the parts at the same time.
Fair enough. And so everything that you see there, that's firmly attached to the base plate?
Exactly. The first part of every build is really important because we have to make sure that the first layers of each build are firmly adhered to the base plate. It's a steel base plate, steel parts, so they will naturally...
So that's pretty much welded to the base plate?
Exactly, it's welded to the base plate, and there are a couple of ways you can then remove the parts. You can use a bandsaw or a more precise wire electron discharge machining process.
And part of the reason, if I'm not correct, or one reason that the parts are anchored to that base plate is because of the residual stress that's built up. Is that correct? Yeah. Residual
stresses tend to build up during the laser powder bed process. So we do have to be careful and make sure that that doesn't affect the start of the build. How do we remove those residual stresses? Well, we can, after this build, we'll be sending the build off to a heat treatment process, which will hopefully equalise all those residual stresses. So as you've seen, we've gone to a lot of effort to try and remove as much powder as possible while the parts have still been in the machine. However, as there are so many complex channels and geometries within these parts, there is still a lot of powder within the parts themselves that you can't see at the moment. So that's where our Solukon comes along.
Fair enough. I take it one of the, I know from my experience, one of the challenges is like removing powder in a standard way. So, you know, it's one time in the olden days you might put these parts on a vibrating plate and just shake them to get the powder out. If you're in production trying to do that over and over again, that's not repeatable. So what we found is at least Solukon have come up with a really neat solution where it provides a standardized method of removing powder.
And the issue with powder removal is that it's actually quite hard to verify that you've removed everything. So you'd have to use sort of borescope techniques or even X-ray techniques to prove that you've removed all the powder from these builds. So the Solukon is a really interesting solution to do as much of the work for you as possible in vibrating and rotating the build around to remove as close to all of the powder as possible.
And I suppose what's key in that is that repeatability.
Yep.
To be if you give it the same build, every day and just do that same powder removal, does it come out with the same end result? And, as more and more companies move to production, that's really important for them. So this is Andy just now attaching the build plate into the Addup. As you see, we do have to use many pick and go trucks to get the build plate in there. It is quite heavy. I mean, it's probably in the realms of, depending on what's on there in terms of the part itself, between 20 to 50 kilos. I think the machine itself can actually deal with a max part weight of 250 kilos. So it's fairly robust, and as you see from there, it can take pretty decent sized parts, and I believe there's even a extended version which is more tailored for the space market that deal with the longer componentry you see is more typically being built in that industry. Yeah,
the plate by itself was about 40 kilograms, so you add on to that the weight of the parts plus the powder that's still within them, and you're talking serious weight, and that is something we really have to consider moving these plates around.
So what you'll see here is the machine's now inerting itself, so it's pumping argon in, and that's just purely to, you've got a lot of reactive material in there in a tight enclosure, so that's a potential explosion risk. So they're mitigating that risk by doing it in their atmosphere. Also, what's possible with the Solukon is you can program it. You can program it to, in terms of how it rotates, how the frequency it vibrates, and the duration, and that gives you all sorts of abilities to tailor the depowdering to the build.
So here you can see that the build is starting to rotate and the vibration system has been turned on, and you can see in it an unbelievable amount of powder that's still in the build. That's about 2.5 kilograms of powder that is pouring out there into the chamber of the Solukon. In a production process, you would be able to recycle this powder as well. In our process, because we use several materials in this machine, unfortunately, we're not able to recycle this powder. But what in the bottom of this machine is a hopper similar to those that we've seen before, and in a typical production environment, you would be able to then recycle that in the same way that we've recycled pretty much all of the powder that's gone unmelted.
And you should say this has been sped up a bit. The machine doesn't move this quickly.
Yes, to make sure that we've removed all the powder, this is often a multi-hour process, but again, very repeatable from build to build.
It's quite an interesting research possibility, is mapping the resonant frequency of the part when it's not, or when you've achieved complete powder removal compared to when it has powder in it. And that's something we're really quite interested in understanding. So you can, again, when you're in that production setting, just have a bit more of an assurance of, okay, I've removed all of the powder, and here is my check of how I do that, to complement such techniques as Chris talked about.
There are even methods that you can use to map out the internal channels within your parts, and then the machine will then calculate the optimum method to remove all the powder.
And so here, what Andy's doing is he's now just double checking that there's no powder left. And now this is quite an iterative process where he's going to be blasting argon from this nozzle, just double checking is there any powder. As you can see on this first pass, there is a little bit left. And although, when you see that powder cloud come up, it seems like a lot of powder. That being the grams of margin steel that are there.
Yeah, we're just removing the last remnants of the powder that have adhered to the parts, just with a blast of argon.
And so, after he's blasted this, what he's going to do is then run the cycle again, and just keep doing that until he's happy that there's no powder left. Obviously, if you were building lots of these parts, you kept the geometry of the part and the build layout the same, you'd begin to understand that process quite quickly, and you'd know, okay, I need to set it for this length of time, this frequency, and blast it out X amount of times. But as this is a short run, we don't have that data there.
So you can see now that Andy is happy that all the powder is removed from the parts themselves. He can then remove the fixture that's been used to. He can then remove the fixture that's been used to attach the plate into the Solukon, and we can send this plate off to heat treatment. When that's finished, we take them through a GOM inspection step to work out whether the parts are built to the size and specification that we hope for. Following that, they'll be removed from the plate. We'll be using wire EDM process for these parts. And after that, they'll be visually inspected to assess for any defects before being sent off for pressure testing.
Oh, and that's pressure testing with Domin?
Yes, exactly. Domin are really interested to work out whether these parts can compete with the components that they currently have on the market.
Oh, fantastic. And so once we have all of that information, obviously we're going to be writing that up, and to the general public, that's going to become a case study that's going to be on our new NCAM website, which is live now. And even aside from that case study, it's a wealth of knowledge in terms of different AM processes that are on there, our different case studies from previous projects, and also looking at some of our bigger publicly funded projects, information's on there. So I'd like to say thank you, Chris, for all of your information and wisdom today, and also running what was quite an interesting project. What's coming next is we're going to be looking at our new M2 Carbon, and we're also going to be taking a look at our new X-Jet machine. So thank you very much for watching.